Welcome to the course on computer science, the subject operating systems. The topic of interest today is the case study on Windows OS, Windows operating system. In the earlier lectures, we have seen that the computer is primarily comprising input, output as devices. There is a central processing unit, there is a memory, and then there is a control unit. There are only these 5 major components that comprise the computer organization. We have been talking about many architectures. The architecture that seems to be reflecting what we do as human beings as computing is John von Neumann created architecture, which is called the von Neumann architecture. So, what we have done is to see how the computer emulates, mimics the way human beings do the computing as we understand. There is a von Neumann architecture, there is a von Neumann bottleneck, which we have been trying to understand. In all these cases, we do note that there will be different users who will use this set of 5 components that make the computer function, and they will have to share the resources. To make sure that the sharing of the resources will be smooth and seamless, there is a reason to believe that some code called resident monitor must be there in the memory, even if it means that some portion of the memory is always taken away by the operating system in the form of resident monitor. Only the remaining memory is used by the programs to store the programs, to store the input data, to store the output data, and then make use of all the other registers in the central processing unit, the clock, and the way the buses function. The entire architecture is used in this manner. As we progressed, we found that there will be many more reasons why the operating system should be there, and today we are talking about very easily 18 to 20 functionalities of operating systems that have very conflicting demands. The memory manager will have to work very closely with the CPU scheduler, with the IO management, with the file system, with the buses, with the way the programs are being handled, with the way the user keeps on demanding. All these things will have to work together, and the limited set of resources naturally present the conditions where there are conflicting demands. For example, the topics which we have in this subject called deadlocks, the topics which we have in this subject priority, the topics that we have been studying in this subject, namely how to manage the limited number of IO resources, let us say the printers, protection, security. We are all seeing the functionalities always working together to make sure that the return on investment on the operating system, namely the CPU utilization, is very high, the waiting time is less, the response time is very fast, the throughput is very high, and the overall user satisfaction is very high. To make sure that all these 5 parameters are happening, we need to design the operating system in a manner where these 18 to 20 different functionalities of the operating system work together in tandem, and there are conflicting demands. Therefore, the concept of these 18 functionalities or 20 functionalities remains the same, but the specific implementation differs. Windows operating system has a set of designers. They have taken certain decisions, design decisions, saying that under the conditions where this functionality has a context which is conflicting with 2 or 3 other functionalities, Windows operating system will decide like this. In Windows operating system will function like this. So, therefore, multiple functionalities having the same shared resources, facing the conflicting design constraints and the way the users demand, have different ways of addressing those conflicts. One cogent set of addressing conflicts and building a functionality to make sure that there will be ease of use, there will be user satisfaction, there will definitely be maximized throughput, minimized waiting time, maximized response time, maximum CPU utilization, we have the Windows operating system. The design principles of Windows operating system are therefore different, and what we intend to do in this particular chapter to explore the principles upon which Windows is designed and the specific components involved in the system. We need to also note that software has very few design rules and design principles that are operational. So, what we are talking about as the principles of design are primarily based on what are called resource management and the constraints that the operating system designer faces. What happens if we have virtual memory which is showing some error, exigency conditions, exceptions? Those are certain things which are very specifically handled in a manner where the Windows designers have made it handle. Different operating systems may have the same functionalities at the conceptual level, but the implementations differ. They look at the same shared resources, they are looking at the same organization, they are looking at the same architecture, but the implementations change. To explore the principles upon which Windows is designed and the specific components involved in the system, to understand how Windows can run programs designed for other operating systems, to provide a detailed explanation of the Windows file system. Ever after the design of the other operating system Unix has blossomed around the idea called file system, we have been talking about many operating systems concentrating on the design of file system. Everything is stored in a file. The user stores the program in a file, the input data is in a file, the output data is in a file. Therefore, file system and its efficiency, that is, given the name of the file, how does the operating system fetch the exact file, the exact location efficiently from wherever it is, whether it is in the main memory, whether it is in the cache memory, or whether it is in the secondary memory or anywhere in the network. Given the name of the file and what we are now calling uniform resource locator, the file should be fetched by the operating system. Windows has internet capability now, and therefore, the file system management has attained a primary focus in many operating systems. But the roaring success of this idea is traced to Unix, which is the next case study. To illustrate the networking protocols supported in Windows, we need to understand that the operating system only has a functionality called networking functionality, but the actual networking is implemented through a set of protocols which are defined and specified by the International Standard Organization Open Systems Interconnect ISO OSI reference model, where there is a physical layer, there is a media access control layer, there is a data link layer, there is a network layer, there is a transport layer, there is a session layer, there is a presentation layer, and the application level layer. What we are doing is the fact that the application comes at a very high level and the operating system is expected to take the other layers which I have mentioned, which are forming the reference model. Therefore, the networking functionality of the operating system comes into sharper focus to ensure that we are able to track what is being sent out of the machine, what is coming into the machine with reasonable degree of confidence and verify. To cover the interface available to system and application programmers, how do the people interact with the system? The application programmer now has to use the system. Essentially, what we began with is there is a hardware, limited resources. We wrote a software, a system software called operating system to govern, to manage these resources. On top of it, we write applications. The functionality of the operating system, the expectations on the operating system have grown significantly from the early days of a resident monitor, and today we have many implementations. Windows is one case study. That is how we have been working on the operating systems. Windows is a 32-bit preemptive multitasking operating system for Intel microprocessors. We now have 64-bit versions. In a sense, whatever Windows does, the bit size is 32-bit. 32-bit is a very big exercise for shipping it onto the buses, for shipping it onto the registers. 64-bit is even more for intensive graphic applications. The more the bit size, you can handle that much fast. Imagine that I need to handle 32 bits as 1 bit by 1 bit. Even if handling 1 bit takes 1 hour, 32 hours are spent handling only 1 bit. If I can have the machine tackle all 32 bits, we will finish it off in 1 hour. These are certain simple numbers that I am talking about, but the point is handling bit by bit is difficult, it is time consuming. Handling a chunk of such bits like 32-bit, 16-bit, 64-bit makes it more efficient in terms of transferring the data from the memory to the registers and back. For example, as we have been talking, the von Neumann architecture warrants that everything is in the main memory, and from there it has to ship into the registers. Back and forth, we will not spend more time on simply transferring the data from the main memory to the CPU and use the buses. The key goals of the system are portability. All Windows operating systems should behave the similar manner wherever they are. That is called portability. If somebody says this machine is having Windows operating system, everything is the same as it was in other machine where I was using Windows. POSIX, this is the portable operating systems interface compliance. Most operating systems thrive on providing this interface, a standard interface to the application program designer. However, the actual implementation of these aspects differs in Windows. Windows is a very unique design. The most striking aspect is the way the designers have addressed the user interface. Some of the most popular user interfaces which were compared always rank Windows on the higher side. It is necessary to understand that the people who are programming, the people who are writing the systems program are well versed with these ideas. However, a simple user, a person who simply wants to get some task done, is not likely to understand the entire operating system and work. He has his limitations, his focus is on the task, therefore we will go ahead and then use only that particular aspect of the operating system that enables me to do my task. If I know that all these tasks will be performed exactly, I can make something happen, but the users are also not too clear what exactly they want to do. So we need to provide a very good interface. What ranks very high is the graphical user interface, which in its initial stage was windows, icons, menus and pointers, WIMP, and this W is Windows, and that Windows operating system name got stuck because we see Windows. Right now I am using a single user, single window. Whereas I can simply say that, for example, minimize the window like this and I am seeing a different desktop. All of you are seeing a different desktop. I can as well go ahead, launch some other thing on a window. This is what I wanted to demonstrate. I can simply say that right now I am not so much keen on using my PowerPoint presentation, but I am trying to see how a web browser can be launched. It is not connected to the net, it does not matter, but I know it is not connected to the net. Instead of locking myself only with a single user, the same interface showing my PowerPoint presentation and worrying about whether the network is connected or not, I can simply minimize this window, take up the browser, launch the browser, find out whether the net is connecting or this particular site is not connecting. I can minimize the window, I can go ahead and see what are the other application programs that are there. For example, I can simply go ahead and launch a notepad. I can say that this is a notepad test. I have the keyboard here. This is a notepad test. So, the last few minutes I have not used the PowerPoint presentation, and what I know for sure is that this machine has many more resources. Simply using it for a PowerPoint is an inefficient use of this machine. because it is very powerful. It is a 32-bit operating system. What I am using is only for the Windows, and I know I have many tasks to do. For example, to illustrate how to use a notepad along with this, so I can see how nicely I can do that. I can do some exercise notepad. If it was connected to the internet, I would have sent a mail, because I know for sure that this particular window is there, it is dormant, and now I am going back to the slideshow. I can as well launch it like that and then move forward in this manner, where I can go back to the slide where I have left. This particular exercise indicates that instead of a sequential single user interface where a user is doing only one task at a time, I can think of creating some windows. Whichever window is activated, an event occurs, that will be automatically tracked by the Windows operating system. It is generically called graphical user interfaces, but the earlier version, before the graphical user interface GUI became famous, we were only talking about what is called the Windows icons. There are so many icons. Once again, I can do that exercise. We can simply tell that we have had another way of minimizing this. End show, we minimize this. Windows I have illustrated, so many icons are there. You are able to see an icon for a computer, you are able to see an icon for the internet, there is a recycle bin icon, there is a Google icon, there are so many files on the desktop. All these are visible. Windows, icons, menus. This is what is a menu. It's a big menu that is coming. It's a start menu, which is a very fundamental menu. Windows, icons, menus, and pointers. See, this is a nice pointer. The mouse pointer is moving. So we addressed all these four as separate ideas. It was not so easy to put all these interface elements together to call them WIMP interfaces. In the beginning, people were not too sure, but the runaway success of Windows operating system made sure that today all users are expecting what are called graphical user interfaces. Now GUIs have become very, very advanced. There are so many aspects of GUIs which is a separate subject by itself. All of them are based on those four simple interface elements which I have illustrated. Pointers, the mouse pointer is moving, I can simply point and click. Gradually, using these four basic elements, we have built a theory on graphical user interfaces. It's a subject by itself. A lot of people are studying that subject, and it's still many more ideas that are going to happen in the field of graphical user interfaces. The interface devices have improved a lot. We have spoken about sensors, we have spoken about completely different input and output devices. They need not be like what I am saying. The mouse also need not be there. The computer has also changed the way it is happening. We have wearable computing. This coat can be a computer tomorrow. There is no need for this much of a computer in front of the desk, in front of the user. So we have been talking about all these simple ideas put together. Some design decisions have been taken, and Windows is now a commercially available operating system that has phenomenal international support. It has compatibility with MS-DOS, MS Windows. MS-DOS had a very, very rudimentary user interface. Windows has stolen the entire market in the sense that it has come up with a very simple, elegant implementation of Windows icons, menus and pointers, quick time. The functionalities are all very clear, crystal clear. It is not talking about providing everything under the sun. It does exactly this much, and when in doubt, it crashes. That's all it happens. If the operating system is not able to resolve, it simply crashes. It uses a microkernel architecture. It's available in 6 client versions: starter, home, basic, home, premium, professional. Now you know these distinctions have all been blurred. Today we are talking about Windows as a default operating system. Whatever supports the Office package, that is good enough for us. However, there have been several client versions called starter, home basic, home premium, Professional, Enterprise and Ultimate. What is it that we need to understand is, for the starter version, it is a very lightweight, very limited implementation of the functionalities. We don't have all the 18 functionalities happening. Half of them will be operational. Even those functionalities are not going to be completely implemented as comparable to the Ultimate. It's a case of how much you want to spend, how much of memory you want to reserve for the operating system. The more the functionalities, the more the capability of each functionality, the more memory it demands. Available in 3 server versions: standard, enterprise and data center. So Windows now has a 32-bit, 64-bit. There is no reason to believe that if you have the investment capability, you can make every client an Ultimate client. You can have every machine on the desk as a 64-bit. It's a case of your finances and your budgeting. 88 it was, Microsoft decided to develop a new technology, NT, portable operating system, that supported both OS/2 and POSIX APIs. POSIX was primarily groomed out of the Unix operating system, and it became a very good standard interface because it assures portability. Wherever there is a POSIX compliance, all commands run similarly with the system. The system APIs are standard application programming interface. Writing the application programs becomes very quick and very fast, very efficient. Otherwise, we have been talking about whenever the operating system is going to be released, we needed what is called a software development kit, SDK, which only talks about interfaces that are specific to that operating system. Then you will have to wait for the operating system to be ready, commercialized, ready to release. A few weeks before the operating system is ready to release, the SDKs will be downloaded and the application programmers will have a little bit of lead time. There is no need for making the interface so different for any given operating system. So Windows decided to make a new technology. Everything in Windows new technology, Windows NT, was very cleverly designed, very sleekly packaged. The entire file system was also changed. It is called the NTFS. Talked about extensibility. All functionalities are around the microkernel, but then if you don't want a few functionalities, you can simply cut out those layers. This is the trick which they play in making 6 different client versions, 3 different server versions. The architecture is layered architecture, and what we need to understand is the fact that we do not need all functionalities for all flavors of this window. If it is basic, if it is a very limited capability Windows, it has only few functionalities up to a point. The layered architecture has always given us this particular capability. Portability has already been mentioned, reliability, compatibility, performance. So when we are taking design decisions, when functionalities are conflicting with one another, what is the rationale for designing? Windows operating systems designers have opted for extensibility as the number one, so that they will have different clients at different prices, different sizes, different demands on the machine. Portability, we need to understand that it will be platform dependent code isolated in a dynamic linking library, otherwise everything else is platform independent. Reliability, compatibility. So we have the way of looking at reliability, we have compatibility, we have performance, preemption of low priority threads. We need to understand that when some program is being executed through the operating system, if a higher priority program comes, what should we do? Should we have the higher priority program waiting and execute the lower priority work, or should we close the low priority work, finish off the higher priority program and then make it happen again? The low priority one comes back. This is the idea which is different in Windows. We call the idea implemented in Windows as preemption. If one job is running, there are reasons to believe that it can be halted, put out of the execution phase, execution state, bring another exercise, another task, complete it and then go ahead. This is very necessary because we are talking about multiple windows. There is not much of a work happening in that Google browser that I have opened. I am hoping that will connect to the internet, therefore it is of a low priority. It can be halted if some message comes from that window, it can be halted for some time because I am not interested. Right now I am doing the same thing, I am giving more priority to this. There is that Google window which is there, but it is not active, it's on a low priority. I can go and pick it up whenever I want to make it prioritized. Symmetrical multiprocessing, we have been talking about multiple processors, we have been talking about core chip, 4 CPUs will be there, 4 CPU cores will be there. It has phenomenal international support, wherever you go it's Windows. Now we have the native language support on the interface, you get the Chinese interface, you get the English interface, you get plenty of interfaces on all those things. Then we have had Windows architecture, it is a layered system of module, there is a protected mode, some portion of the code is protected. The hardware abstraction layer, which is what is the Windows really talking to. The Windows is not directly talking to the hardware, it is talking to a hardware abstraction layer which is presumed as the architecture that makes Windows very efficient. It is tailor made, the Windows operating system is tailor made for this hardware abstraction layer. Anywhere where this HAL is valid, on that machine Windows will run, giving you precisely the same results, the same interface, the same way of executing, the same way of working, and these are working in a protected mode. Whatever happens, no program will intervene with the protected mode, it is very clear. Therefore, your core resources are not going to be worked upon by unauthorized users, by unauthenticated users, either accidentally or intentionally. In a sense, protected mode of operations is the maximum measure which we can take to ensure good protection and security of the core ideas in Windows. User mode, this is out of the system, collection of subsystems, it has protection subsystems, it has many other things to talk about. Next comes the depiction of the architecture. So, I am zooming this, this is what it is. The architecture is going to be a logon process, a security system, authentication package. Please understand that we also have an OS2, we can have a Windows 16, we can have Windows 32, we can have MS-DOS, we can have POSIX application, all running in different windows. Win32 will take care of any operating system with this kind of an architecture, and please understand that once it is outside of the, this is the user mode, this is what we are talking about is the user mode, and once it is out of the user mode and into the protected mode, the system mode, the hardware abstraction layer is here, the object manager, security, process, plug and play manager, all these things are not in the user mode. The user mode closes here, the protection mode, the system mode starts here, the hardware abstraction layer, the kernel, all these are well protected. So, this is what I have been talking about, and once we see this slide, we will understand that the Windows architecture is like this. It is a layered system, a user mode and a protected mode. Any layer can be used, any functionalities can be chosen. We talk about a nice design which gives us the flexibility of having so many things, so many flavors of Windows, that is a client version, a starter version, a home basic version, a home premium, a professional, enterprise, and we have the ultimate. It suits your purse, it suits your system configuration, as long as the configuration is comfortable with the hardware abstraction layer, it is enough, the Windows will run. The runaway success of graphical user interfaces is due to the operating system Windows. Thank you.